Great. So welcome to Yotam. Let's go.
Yeah, okay. Thank you, Reed. Thank you everybody for joining me today. Where to start? So this talk I'm going to tell you about the construction of high dimensional expanders that are both very sparse. And the construction, I feel it's somewhat simpler than the known constructions today. But I'll tell you about this more later. This project is joint with Cayley, which is a postdoc here and in Dimax, and with Avi, which is in the audience. So you can also ask him questions. So I'll start with actually, defining what high dimensional expanders are, and then we'll kind of move on from there. So probably most of us know expander graphs. These are these fundamental, well-connected pseudo-random graphs that appear everywhere in combinatorics, theoretical computer science, and so on. And high dimensional expanders are our attempt to generalize this notion of expander graphs to hypergraphs and other set systems. This notion has already shown promise in theoretical computer science in like many interesting applications. I will tell you about maybe one of them. But kind of contrary to just expander graphs, we don't know a lot of good or bounded degree constructions of high dimensional expanders. And while we do know some families of these objects that are bounded degree, it's still, we're kind of attempting to construct more of those that will actually help us kind of understand what's going on under the hood in these objects. So today I'm going to tell you about, again, a simple such construction. It won't be bounded degree, but it will still be kind of non-trivially sparse. And to understand it, we will only need linear algebra. So let me start with actually talking about expander graphs. So in this talk, all my graphs are going to be regular. So let's call the degree of a vertex capital D. And I will use the spectral definition of expansion. So let me denote the adjacency operator, the normal adjacency operator of G, to be this matrix that's indexed by the vertices in the rows and columns, and AG at some point VU is just going to be 1 over the degree if V and U are neighbors and 0 otherwise. And you can see that this matrix, all its rows sum up to 1. And so its largest eigenvalue is going to be 1. Just if you take the constant vector, it will be an eigenvector with eigenvalue 1. And so all the rest of the eigenvalues are somewhere between -1 and 1. So in particular, we denote by lambda G the second largest eigenvalue of this matrix. And it's smaller than 1 if and only if the graph is connected. Some of you probably know this. So the definition of expansion that I'm going to use in this talk is the two-sided spectral expansion. And it's as follows: let lambda be a constant. We say that G is a lambda expander or lambda two-sided spectral expander if this lambda G is less or equal to lambda. So I'll just comment, if you've seen other definitions of expansion with outgoing edges and so on, it's okay to think about these. They're mostly equivalent up to this one-sided, two-sided technical details. If you know this definition, then it is quite standard. And if you haven't seen any definition at all for expansion, let me maybe tell you why or what I think about expansion.
By second largest, you mean in absolute value?
Yeah, in absolute value. Thank you. Yeah. So here's my.
That's the meaning of the two-sided.
Yes.
Right.
But you wrote the one-sided.
Exactly.
Right. That's why Ramon gave me the comment. I forgot to say it. I meant in absolute value. Okay, so like when I say second largest in absolute value, I mean that if you look at the negative eigenvalues, like if it has an eigenvalue of -0.9, so the second largest eigenvalue should be like 0.9.
In particular, it's not bipartite.
Yeah, exactly.
Then you should also write it in the definition. You want lambda of G to be also bigger than minus lambda.
No, if it's
I
an
wrote in
value,
absolute
you don't need it.
value, but I
No,
don't.
but in the definition. Okay.
Yeah, you don't
I think it's confusing.
Lambda G is the second largest of the absolute values of the eigenvalue. It's always positive because it's an absolute value. So it's more.
Okay.
Yeah, do you want me to write here greater than minus lambda? It's not.
No, it's up to
No, no,
you.
no.
Which one do you prefer? Say either this or that.
No, lambda of G is defined to be a non-negative number. And so that's enough.
Okay, let's be entirely explicit, okay? I said that the first eigenvalue is always one, and you can see, because this matrix is real and symmetric, that it will be diagonalizable, and it will have, say, n eigenvalues if the number of vertices is n, and they will all be less between this one and minus one. And when I say that I want a lambda expander, I mean that lambda 2 up to lambda n will be between this constant lambda and minus lambda. Okay, so just so that there will be no confusion. In any case, I kind of want to give an alternative definition that I find nice. Let me denote by Kn naught the complete graph with self-loops. So all my graphs in this talk will be simple without self-loops except for this one. And it turns out that if you look at this lambda G, one other way to kind of define it is just the difference between this adjacency operator of G and the adjacency operator of this complete graph with self-loops in operator norm. And even if we're not remembering what operator norm means, this is basically measuring some distance between the graph G and some very dense and well-connected graph. Like the complete graph with self-loops, right? Every two vertices have an edge, even a vertex with itself. And so when we say that something is a lambda expander as lambda grows smaller, this really means that our graph is somehow closer to this complete graph. And indeed, a lot of phenomenon that happen in this complete graph will start to happen also in our expander graphs. For example, the diameter of G will be very small. It will maybe only be logarithmic in the number of vertices. Random walks inside G will converge very quickly to the uniform distribution. And in general, there are a lot of things that we know on expander graphs. And our model is, whatever happens here should happen also in our expanders. However, having this noted, also a very classical theorem tells us that we can find expander graphs that don't need a quadratic number of edges like in the complete graph. We can actually find them with a linear number of edges or bounded degree. So in particular, for every positive lambda, there exists some degree d, which is roughly 1 over lambda, and a infinite family of the regular lambda expanders. And this is actually known to us for several decades, but still I think it's kind of surprising that this is like a very dense graph, and we can kind of approximate it using very sparse graphs. So who proved this theorem, or where can we get sources of expander graphs? I like to divide them into 3 sources, kind of random constructions or random graphs, group theoretic constructions, things that come from like properties of groups, and maybe more elementary constructions. So I'll write here combinatorial and linear algebraic. And so even in the 70s, Pinsker observed that random regular graphs are excellent expanders. And in fact, Alex Lubotsky told me that even in the 60s, there is some work by Barazdin and Kolmogorov
For Rasdin only. I'll give you the history later.
Okay. I allow me to write him because
You like combinatorics, that's fine.
yeah, thank you. Which also looked at expanders, like in their paper, they don't really define it. They look at some kind of embeddability of graphs and they lower bound something that kind of depends on expansion there. And in the process, they kind of show that almost all graphs are expander graphs. So I find this interesting. However, you know, in theoretical computer science, if we actually want to use these graphs, we need explicit constructions, especially if we maybe want to use them for de-randomization. I think that the first explicit construction is due to Margulis, and I'm writing it here in like this group theoretic category because Margulis observed that if you take a group and it has some property on its representations, then actually you can look at Cayley graphs of these groups or maybe their quotients, and these will be very good expanders. And this kind of paradigm of looking at groups, seeing some group theoretic property and translating it to graph expansion was later even used to kind of give the optimal expanders, the Ramanujan graphs, which kind of are optimal in the trade-off between how low we can take this D and how small we can take this lambda. So Peter is here, so I should write Lubotsky, Felix, and Sarna. Thank you. Which actually constructed these Ramanujan graphs. However, as combinatorists, sometimes we want to understand expander graphs without actually translating things to group theory. So one can ask, you know, can I actually construct an expander elementary and in an elementary manner and like analyze it in very elementary manners without any kind of magic that's coming from group theory? Of course, this is a soft question, right? It's not anything very mathematical, but here we also have such constructions. So maybe I should mention the zigzag product by Reingold, Banan, and Avi in, I think, 2000. So this is the product. Gil Cohen told us about it earlier this semester. And kind of what's nice on this about this construction is that you start with a small expander, and then you do kind of operations that like inflate the number of vertices, powering to keep the expansion. Then you kind of do this zigzag operation to like to make the number of edges still constant, and you like slowly grow yourself a family of expander graphs. And maybe the last thing that I want to say about these constructions of expanders, that any construction of expanders that we got, it taught us about expander graphs, but sometimes it taught us about other phenomena as well. So for example, this phenomena of like random graphs being expanders, later people studied it and really tried to optimize it, such as Friedman's theorem that showed that random graphs are also almost optimal expanders. Ramon gave us an excellent talk about this as well. And like a lot of techniques of like studying random graphs eventually kind of evolved and gave us, you know, other ideas of how to study other random processes, such as, you know, strong convergence of matrices. If you talk about these combinatorial or linear algebraic constructions, maybe I should have mentioned that kind of, I didn't say anything about linear algebra here, but you can also kind of construct very sparse expanders just using error correcting codes. Maybe the degree is not exactly bounded, but still kind of, this also gives you a source of expanders. And kind of because these expanders are well connected with all sorts of algorithms that we like, in the years that followed, for example, this work, people kind of understood that they can take graphs and like gradually also grow them or change them or modify them. So here I could mention maybe Irit's PCP proof, or maybe Reingold's algorithm for solving undirected connectivity in log space, which was a very celebrated work at the time. where in all these works, you kind of take an initial graph and then you kind of do all sorts of modifications to it up until you get the graph that you want. So this is something that like these elementary constructions taught us. And finally, you can ask, what do the group theoretic constructions teach us? I'm not an expert in group theory, but it's actually quite a lot. I recommend Alex's book about this, about, for example, how to sample random elements in groups and mixing and so on. One thing that group theory was really helpful in is actually to generalize expander graphs to hypergraphs and give us high dimensional expanders. Because some of these constructions, you can think about them as kind of taking an infinite graph and then using some kind of group to kind of fold it into finite graphs that inherit some kind of expansion from the infinite object. But if the groups are your focus, then you can kind of replace this infinite graph with an infinite hypergraph or some kind of other set systems and really get other objects that have maybe even more interesting properties than just being a graph. So the next thing that I want to do is to actually.
By the way, I now admire your definition of two-sided, because that way you didn't have to mention Srivastava, Spillman, and Vargas, because they don't know how to construct what two-sided.
Yeah.
I'm just teasing.
That's a good point. I should say, like when I was practicing this, I contemplated maybe I want to do this with slides because there are so many people that worked in this area, and like I'm not doing you a very good service in like actually surveying all of them. So you should keep giving these comments. So now though I want to define high dimensional expanders, and you should note that there has been a lot of attempts to actually generalize expander graphs to hypergraphs and set systems. We've kind of converged on 2 or 3 definitions up until now, but I'm just going to give one of them, which is kind of central, at least from the theoretical computer science perspective, which is sometimes known as the local spectral definition. But let me just start doing things more formally. So we're going to deal with hypergraphs that are called simplicial complexes. So suppose we have a hypergraph X, we say it's a simplicial complex. If it is downwards closed, which means that if I have a set inside X, sometimes I'll call these faces, and I have a subset inside this set T, then this subset is also in X. So here is my favorite simplicial complex. It is called the fish complex. And when I draw it like this, and I tell you I have the complex with these 3 triangles, then I also mean that it has all the 8 edges that are contained in these triangles, and of course all the 6 vertices, which you can think about either as singletons or as the vertices. And in fact, even kind of the empty set is in here, though it's just a technicality.
Can you clarify, X is what kind of object?
It's a hypergraph, sorry.
So X is a family of subsets of some base set?
Yes.
Yeah. And what is the base set? Is finite?
So we will only speak about the finite hypergraphs in this talk. So yes.
Okay.
So you can think about, so you have some V which are vertices, and you have some, maybe hyper edges here, and kind of because the downwards closure property, once you have a hyper edge, you also have all its singletons. So sometimes we just like to think about these as sets without distinguishing between vertices and hyper edges, although formally you're correct, like we need some ground set to begin with. Okay, good. So some notation, I will denote by xi all sets in S that have size I plus 1. This is like a very unfortunate convention, but these objects come from algebraic topology, and there sometimes people care about the dimension of a set. If you look at like its convex hull as a simplex or something like that, so kind of a point is a 0-dimensional thing, an edge is a 1-dimensional thing, and we carry this convention with us. And the dimension of a simplicial complex is just like the largest I can put here so that it's not empty. So it's, maybe I'll write it like this. The maximum set size minus 1. So for example, this is a two-dimensional complex because the largest sets that I have here have size 3. Good. So what's going to be a high-dimensional expander? Basically, if you only want to talk about graphs and you want to think about this as some kind of high-dimensional expander, it would just kind of be a graph where every neighborhood is some small expander. But using this language of simplicial complexes, we kind of can talk about these neighborhoods in slightly more generality. So a link is supposed to be the generalization of a neighborhood inside a simplicial complex. So suppose we have some set in X, its link is going to be all the sets that contain S inside our set, inside our X, inside our hypergraph, but then we remove S. So kind of, let's look at maybe an example here. This is my fish complex. And suppose I'm looking at the link of this vertex E, or the singleton, which contains only this vertex E. So what are kind of the sets inside? So for example, E is contained in an edge with C, right? EC is an edge, so I remove E from that edge, and this is going to be one vertex inside there, and of course, D and F likewise. But we're not just looking at the neighborhood of this thing as a graph, right? E is also contained in this triangle and in this triangle, and if I remove E from those triangles, I will get an edge. So you can see that like the link of this vertex E or the singleton E will actually look like this. 3 vertices and edges between them. So it's like a 2-patch. Of course, other links in this graph will look differently, and that's okay. So in particular, if we have a set that's not too large, we can consider the link graph which just contains the vertices and the edges that are inside the link. So most of the time I will just refer to this graph, although formally it's a simplicial complex, right? And the more kind of the higher dimensional, the original simplicial complex, the more structure we have on the link. So again, this is just generalizing neighborhoods. Great. So this is almost all the notation I need. And now I can kind of go to my central definition in this talk, which is going to be high dimensional expanders. So a D-dimensional simplicial complex X is a lambda high dimensional expander if every link graph is a lambda expander. Okay, but formally.
Now your link graphs are not necessarily regular.
Right. In the constructions that I will talk about today, they will all be regular. Formally, if they're not regular, I kind of need to modify this definition of expansion, and maybe just believe me that I can. But that's a valid part.
Sorry, what is D?
Sorry, yeah. So the dimension of X is like
D is dimension of X?
yes, so so a D-dimensional simplicial complex, I meant that like X has a dimension D, so like the largest.
Oh, yeah, I understand what dimension it is, yeah.
Yeah, it's just that, so the D above that is the same as that D. That's the question, like if I is less than or equal to D minus 2, so that's the dimension minus 2.
Yes. Oh, thank you. Right. Great. So a D-dimensional simplicial complex is a lambda HDX if, even ignoring all these like numbers, whenever I can define a link graph, this graph is an expander. So if for every I less than or equal to D over 2 and S inside of Xi, the link graph is a, I'll say non-empty lambda expansion. So just to be very explicit, if I look at a two-dimensional simplicial complex, I'll call it a lambda expander if the link of every vertex is going to be an expander, right? Because like d minus 2 is 0, which means the vertices. Also kind of, this is a very compact way of also requiring the underlying graph of the complex itself to be an expander, because like technically the empty set is also in our complex, and so kind of the link of the empty set is just the vertices and edges in X. But if you don't want to think about this technicality, just think about this as an extra requirement here. So I'm also going to assume when I say a high dimensional expander that like the vertices and edges here are also well connected. This is quite a bad high dimensional expander, right? I mean, it is connected as a graph, of course, but for example, if I look at this vertex C, which is like the vertex connecting between the head and the tail of the fish, right? It is connected to like this bow tie, right? This is how it looks like. So if I take the link, right, it will be disconnected edges, and disconnected graphs are very bad expanders. Kind of the second largest eigenvalue will just be 1. And so this is like a non-example of a high dimensional expander. Maybe the first thing that you can ask, what kind of high dimensional expanders are there? So like the best expander graph, right, was the complete graph. So here we maybe expect that the best expanding hypergraph would be the complete hypergraph.
Can I just ask us a question? I mean, I was trying to see how the ordinary notion of expansion of a graph follows from this definition, but that's d equals 1, right?
Yeah,
Kind of
so,
weird.
okay, yeah, thank you, let's kind of be clear. If this is xi, right, like faces of size I plus 1, I can like technically write x minus 1, which contains the empty set. And if you look at the empty set only, like it's linked, right? It's like just the whole graph. So in a one-dimensional simplicial complex, which is a graph, you just require that this thing will be a lambda expander. And so it's an expander.
So it should be for all I lesser or equal to d minus 2 and greater or equal to minus 1.
Yeah.
Okay.
So like for all I where it makes sense to look at the link graph. Because, right, if I have a edge here, it doesn't make sense to look at the link graph because it only has the vertex. Like you can't even find edges. But other than those like trivial links, I want everything to be an expander. So in particular, it means also the underlying graph. And again, if you don't like this empty set thing, you can just add this as another requirement. Good, that's a good question. Great, so let's look at the example, which is just a complete graph. So I'll call it maybe delta ND. So I write this notation, which is all sets of some vertex set of size capital N of dimension D or size at most D plus 1. Okay, so all sets that are containing D plus 1 vertices or less. So for example, if I have a set S that has, I don't know, size 3, how is its link going to look like here, right? So what are going to be the vertices in the link of the S? Well, all sets of size 4 exist, right? So in particular, all sets of size 4 that contain S and another vertex that's outside of S. So this is just going to be, you know, n minus 3 vertices. And what about edges? Well, all sets of size 5 exist in my graph, at least if this D plus 1 is equal to 5 or more, right? And so all edges will actually be in my link, right? So if I look at, it's just going to be all edges. Of course, vertices don't have edges with themselves, but other than that, it's okay. So we see that we have here a clique. And maybe you should believe me that the clique is an excellent expander, at least if I have many, many vertices. So maybe think about n is large.
Follows from the definition.
Yeah, I mean,
Number
technically,
zero.
so I said here that I need self loops, And,
It's almost zero.
but it's almost zero, right? It's like 1 over n minus 4 in this one. So like, when the number of vertices is large, these loops don't really matter. But yeah, it like almost follows from the definition, but you can just calculate this. It's like a very simple graph to calculate its expansion. So in general, kind of this complete hypergraph is going to be a lambda HDX for lambda that's like 1 over the number of vertices, maybe minus the dimension, because like you're looking at cliques with slightly less number of vertices. So at least if this D is bounded away from n, this is like an excellent expander, high dimensional expander. So kind of in the second part of this talk, I'll use this notation quite a lot, so I'll introduce it now. So I will also say that X is an n d lambda high dimensional expander if the number of vertices in X is capital N, the dimension of X is little d, the degree of a vertex in X is capital D. This is just the number of adjacent edges. Okay, I don't mean higher dimensional faces. And lambda is the expansion parameter. Okay, so this is just notation. And, you know, having bounded degree expander graphs means that I can construct families of n1 O of 1 lambda HDXs, right? These are just bounded degree expanders. And we can ask, you know, can I replace this one with 2, 3, or any arbitrary numbers? So I will tell you everything about that in a moment. But before that, I want to address maybe a question, which is, why do we care about this definition?
Can I ask another question?
Yeah.
It's probably a trivial exercise, but it's hard to see when you see the definition.
Yeah.
What you really seem to care about is the degree of these graphs xs0, xs1. Is it clear that they are bounded by big D if you just assume this on the base?
Sure. This is a good question. Suppose that every vertex is connected to the things,
Yes.
right? Like, then you can ask kind of, you know, what is this D? This is going to be the size of the link inside V, right? Because the number of vertices in the link correspond to the number of edges that contain this like specific vertex V that you're taking its
The
link.
link of the vertex.
Yes.
Care about links of high dimension.
Sure. Let me.
Yeah, okay. Yeah.
Okay, right, it's like the number of edges. And so, for example, if I look at the link of the edge, right, it's like looking at the link of the vertex, and then inside that link of the vertex, looking at the link of this vertex. And so if in total the number of vertices here is at most D inside the link of the vertex, the neighborhood of this edge inside this link graph, which will correspond to the number of vertices in the link, is also going to be at most this capital D. Right? I mean, every you know face that contains this edge, in particular, it contains this vertex. So it's just going to shrink. And kind of in the context where we want things to be bounded degree, you know, you can also say once, you know, the number of edges are bounded, then also, you know, the number of triangles and so on, at least if you think of the dimension as constant.
You have a simplicial complex.
Yeah.
Figures are
So, and even not, like you can look at, you know, 2 to the D or something like that. You also get some kind of bound on, you know, the number of higher dimensional faces that contain a vertex, in particular, the number of higher dimensional faces that also contain larger sets. So
You don't need this. The previous argument shows that.
Sure.
Yeah, there's no,
But-
that's actually, I find
That's-
confusing.
Okay.
It's no
Degree can only go down in higher dimensionally.
Yeah, that's fair. Yeah. But that's a good point. Like we do care about maybe sizes of a lot of things. Sometimes actually we even don't. Like this is really the measure of complexity that, or the measure of sparsity that we want. And for example, Mitali did an excellent talk about like constructing PCPs and so on. And they're like in their construction, they kind of really mainly cared about like degrees of vertices, even though they're using like expansion properties that come from like higher dimensional expansion. Well, as I said before, there are several attempts to generalize expander graphs to higher dimensions. I like this spectral one. It's simple to work with. It takes a while to maybe get used to, but once you're used to it, it like has some beautiful recursiveness to it. But if you haven't heard about these things before, this is kind of my philosophical paradigm, that if you take lambda to be kind of close to zero, then this implies that the lambda high dimensional expander that you're looking at, it's kind of approximating this complete complex or this complete graph. I don't have this like nice operator norm definition that supports this as
You have it for willing. You can just repeat it for willing.
Sure, that's a fair point. But you know, I'm looking at like maybe collections of these things, so maybe, but that's true. But I want to say that kind of a lot of phenomena that happen in this complete complex, if X is a sufficiently good high dimensional expander, it will also happen here. And kind of one example that I like to give is a mixing of random walks that happen on higher dimensional sets. So kind of, if you look at the graph, right, we always consider this random walk where you start at the vertex, choose one of its edges, and then traverse to the next vertex, and so on and so forth. In high dimensional expanders, you can look at other types of walks where kind of your elements that you're walking on are not vertices anymore. They can actually be higher dimensional faces. For example, I can look at a walk where I start from an edge, go up to a triangle, and then go down to one of the other edges in the triangle. Or even I start from a triangle, forget two of its vertices, go down to a vertex, and then go to another triangle that contains that vertex. And these are sometimes called the up-down walk or the Glauber dynamics or something like that. So in particular, one can maybe look at these walks or these actually graphs where the vertices are now sets of a certain size and the edges are maybe odd pairs S1 and S2 so that their intersection is a certain size. So maybe one vertex less. Right, and these are called sometimes Glauber dynamics or up-down walks. And if you look at the walk that comes from this complete complex, this is basically a Johnson graph, which is a classical graph that people know all about. They know its spectrum, they know kind of what are the worst expanding sets, coloring, and so on. And it turns out that if X is a sufficiently good high dimensional expander, then in fact, the spectrum of this walk in X, and in particular, the second largest eigenvalue, will actually be very close to the spectrum here, for example. And in particular, this walk will actually mix kind of fast if you take a high dimensional expander, provided that this K is maybe not too large. I think that the first that maybe thought about mixing of this walk in high dimensional expanders were Kaufman and Mass. And after that, there was work of Dinur and Kaufman and Oppenheim that kind of found the optimal bounds for this walk and really showed what I just said. But it turns out that all this fact alone is already useful for a lot of applications where you can kind of embed your problem in this Glauber dynamics random walk. So I think that one very nice application of this is the work by Anari et al. On sampling random bases of matroids. So this is Anari, Lee, this is Kikili, Weiss, Haran, and Vincent in 2019, which gave us a randomized algorithm to sample and I'll say approximately uniform or approximately, okay, yeah, I'll write uniform here, but I'll say something. Matroid basis. And I'll explain what I mean. I'm not going to define what a matroid is. It's basically some kind of set system that abstracts properties of independent sets in vector spaces. But here's one example of a matroid. You look at some graph H, and your matroid is the set system that contains all subgraphs of H that are acyclic, that contain no cycle. So let's call them sets of edges in H, so that S has no cycle. Let's call this X, so forests and trees. And this is a simplicial complex, like the top level faces are trees. And if you have a subgraph that contains no cycles, you take a subset of its edges, it still doesn't contain any cycles. So this is maybe just one example of a matroid, and these things are more general. But like even in this tree question, you can maybe ask, given a graph H, how do I sample a random tree inside? There is some stationary distribution here that I'm hiding, but don't think about it. Think maybe just about a uniform at random tree inside H. It's a question. So let me describe a very simple algorithm that can maybe do this. You start with a non-random tree. Maybe you found it by, I don't know, Kruskal's algorithm or something. And now we're trying to like gradually randomize it. So maybe we remove one edge from this tree. Now we get kind of a forest and we have two connected components in our graph. So now let's add another edge that connects between these two components. Maybe it's the same edge we removed, maybe it's some different edge, I don't know. When we get this T1, it's also not very random-like, right? Like we have here some arbitrary T, and this T1 has almost all the edges in T0. So how can we maybe get into a more random tree? Let's repeat, right? So maybe we go kind of remove one element and add another to get T2, and so on. And one thing that's interesting is that you can ask, how long will this process take to actually converge to a random tree, right? Because if I'm going to continue doing this again and again, I am eventually probably going to lose all the edges here unless some like very improbable event happened. But you can ask, like, how close is this to actually giving me a uniform distribution? Or, how far do I need this M to actually take me? And it's not even obvious that you will maybe get a tree that's like appropriately distributed here, even if like you take a huge number of steps. But it turns out, and this is like the main insight in this work of Anari et al., that if you look at any matroid, then X is a high dimensional expander. There is some technical caveat here, one-sided, two-sided, but ignore that for a second. This simplicial complex is a high dimensional expander. And this walk that I described to you is just the walk where you go from K set to K set by like removing one element and then re-adding it, which is exactly this like triangle edge, triangle walk that I described. And so using this alone, they show that this walk mixed fast. And in fact, you can take number of steps that's like polynomial in the number of vertices of H and already get something that mixes quite close to a uniform tree. So I don't want to write the exact formalism here.
Nothing sparse in what they're doing, right?
Right, so here they don't use anything sparse. Like matroids are automatically very, very dense because...
No, they are not very dense. They are not very dense. It's an exponential size graph.
Sure.
Complex, and the degree is polynomial. It's just a number.
No, why is that true? Like if you look at
only one element. neighborhood.
Oh, in this,
Yeah, but it's not.
right, but if I look at like the degree of like a single edge here, it's not going to.
Ah, no, you don't take the gift. I mean, the works are, yeah. And that's what you want in general in global dynamics, that you can find
Yeah.
a neighbor
That's,
quickly.
sure, that's,
Yeah, but it's not bounded degree.
right,
Yeah,
it's
not bounded,
definitely,
it's like
it's
polynomial.
definitely not bounded degree. In this,
No, but it's highly not trivial because
No, I'm not-
the scale of things
Yeah.
is not obvious.
it's-
not taken.
yeah.
yeah, this is, that's a good point. I want to say maybe like, this is maybe my easiest application to state. Of course, Mitali told us about PCPs that you construct using high dimensional expanders like these. And there are many more applications. In general, even in expander graphs, like you can kind of divide your applications into things where you get to kind of pick the graph and then you maybe want it to have bounded degree and maybe other properties. And things where, you know, the graph is given and using its expansion properties, you want to say something. So this is more like the second kind of application.
So just a random question, but you could do this walk where instead of deleting one edge, you deleted multiple edges.
Yeah.
In general, does that like mix faster than just deleting one edge?
Yes,
Yeah.
yes.
Okay,
The
but
more
then
edges
here you
you
can't do it because you would need to be able to compute, say, like after deleting 5 edges
Sure,
or
I mean,
edges.
yeah, I mean, you can do it with 3 edges, right?
Three
Like it
edges,
won't,
sure.
a constant number of
Yeah,
edges
yeah,
you won't
right.
mind, but
Since I want to learn, what is Kruskal's algorithm?
oh,
It's probably for a different.
yeah,
Offline.
I'm
like,
showing, firstly, it's not Martin Kruskel.
sure, it's
Is it Martin Kruskel or his brother? What's his first name?
Oh.
I'm sorry, I don't.
Probably, yeah, offline. is
Yeah. But like you start with an arbitrary tree and you can imagine that, you know, if you don't want to sample a tree, just want to find a
Yeah, just
tree,
find it.
then just find it. It doesn't matter where you start. That's like that's
It
the,
gives you an algorithm to find a tree.
yeah, and Kruskal even like
No,
a
no,
minimum.
Kruskal. Kruskal is for minimum.
Yeah.
You just find the tree.
But how?
What?
But how?
You want to that first. That you want to.
Yeah, you can also do beer. No,
It's yeah.
I was trying to, you know, just if somebody thinks for a second, you know, how do I find the tree? So I hope that people knew this algorithm, and if not, now I feel remorse on that. Okay. So yeah, so maybe let me tell you about constructions of high dimensional expanders. And this will kind of conclude the introductory part of the talk. So as in expander graphs, I want to construct, you know, these n, b, b lambda HDXs. And I can think about, again, these 3 sources of constructions that I had in expander graphs, and let's see what happens in HDXs. So I have random, I have group theoretic, and I have these like combinatorial and linear algebraic constructions. Yeah, and let me just tell you what we know. So group theoretic constructions, as I said before, you can take this paradigm of like quotienting some infinite object, and in fact, we know today of another source of these things that you can think about them maybe slightly differently. So here, maybe if I will do a table with dimension, expansion, and degree. So group theory really gives you all you want. You can have any dimension, any expansion, and degree of 1. Of course, this depends on, you know, which lambda you want to take and which dimension also that you want to take. The higher dimensional the objects will be, the higher degree you need to take. But given a certain dimension and expansion, this is fixed. So I've learned that the first to actually consider such objects was Valentine in 2000, at least I think for dimension 2. And the motivation behind her work, and actually a lot of works that followed, Cartwright, Solend, Zhuk, Lee had a construction, Lubotsky, Samuels and Vishne. I'm sorry that I'm not writing everything on the board. It's truly a lot. And the idea behind these constructions is to say, oh, we know these like LPS constructions of Ramanujan graphs. Let's take an object, an infinite object that's kind of generalizing some infinite tree, and let's look at Ramanujan complexes of that. And you can ask, why would you like to do this? I think some of the reasons was just like mathematical aesthetics and maybe some group theoretic motivation. Here I'm specifically talking about this work of LSV, Lubotsky, Samuels, and Vishne, because in retrospect, I think that Alex Lubotsky really had this vision that these objects are supposed to be interesting and supposed to really have some kind of impact in other areas of math as well. And kind of in hindsight, he was correct. So, but these really weren't the only works that did this. I say that like a decade and a half later, there is also a nice construction by Kaufman and Oppenheim that kind of didn't quotient this like infinite Brought-Titz building. It did something else using Shabbat groups. Anyway, this is just for general knowledge. So now let's try and appreciate this by seeing like what we can do using the other sources. So what about?
Do you have an Alombopana bound here? Like, is it the same as for graphs?
Yeah.
Because in particular, you demand the graph itself is an expanded.
So
They achieve it using these group theoretic constructions.
Yes, the answer is yes.
Can you? No.
But the universal object is this building. And you show the quotients have the same property as the building, and that's.
But I will
Argue? Okay.
I will argue that I care about high dimensional expanders that also don't come from the building. So maybe the universal object is something else.
Yeah,
and
right,
then-
but the ones which, the first two that you have there.
Yeah,
But the
Valentine.
low bound of Alombopana holds.
the lower bound of Alombopana holds, but I claim that the lower bound should actually be some, I think it's kind of simple to show that assuming very mild assumptions, the lower bound of the degree should be at least exponential in the dimension. And I believe that it even supposed to be like 2 to the d squared.
Okay, so it's not 2 squared d minus, there are two separate questions. You can think of Ramanujan as being the spectral gap is bounded by that universal cover, and then these things by definition satisfy them, right?
Yeah.
But you have here a definition in terms of a number lambda.
Yeah.
Or defined as
Yeah,
lambda
yeah,
HDX, and I'm asking whether this lambda is controlled by the lowest order, by 0 and 1, or whether it has to
No,
be worse.
it has to grow worse when you take the dimension higher. We don't know how worse. Like,
And even for the universal building, doesn't get 2 square root d minus 1.
That's the, right,
It gets worse a little.
But this
but the
measure, the analog of Keston's measure is well understood in buildings. This is
Yeah.
very important.
that's
And so that's been computed, that's.
A building is not a tree, right? Unless it's in dimension 1.
So the natural analog of a Lopana would be to have a lower bound that says that it always has to be lower bounded by the thing that you get in this building up to little o1. Is that no?
That's not one. Is it right?
what? No, it's not.
It's very easy.
No, I do not. No, I do not.
It's very easy to see that any finite quotients cannot do better than what the building produces.
Yeah, that's.
And that's basically a Alombopana in this setting.
In the
Yeah,
group theory.
that's.
If you're
Very restricted,
Maybe I will.
I'm restricting to certain.
yeah.
There are actually 2 separate questions here, which is why we're getting into this discussion, right? Like, one question is, you only tell me what you want about lambda and d, and I need to give you a lower bound on the degree. There, an optimal lower bound is not known. I have my guesses about this, but it's an open question. What Peter, you are saying, which is also correct, that if you look at high dimensional expanders that come from a quotient of some building, the lower bound that you will get is like the degree that you will have in the building, and you will say, in this sense, like the optimal lambda that you can get will be something that comes from this building for said lower bound.
It's not clear, the
But-
building is the unique.
Yes, it's not,
object that you could
I mean,
use.
the building is not the unique object that you can work on. We already know about other objects that give us this property. So the answer is actually no. And in general, like, I don't know like a good answer.
So there isn't even a low Popan at the infinite level. You don't even know what is the best building that you can build for the infinite dimension.
Yeah, also, it's not clear that I need some infinite thing, right? I mean, a priori, maybe I have a family of these that are not universally covered by anything, like infinite, of course. So, yeah, it's a good question.
Sorry, can you repeat in one sentence, like, so what is the goal of how are you trying to relate dimension, expansion, and degree?
Yeah, so I'm just going to tell you, like, kind of fix some dimension and some expansion, what kind of degree you can get from like constructions.
For a given dimension and expansion, what is the like optimal degree?
Exactly. Good. Let's talk about combinatorial constructions. So nowadays, we know to construct these of any dimension and bounded degree, but expansion that's either half or higher. So remember, we want lambda to be maybe as small as we want. The smaller it is, the stronger the definition. But using kind of simple, take a graph, tensor it with a complex, do some operations, we can only get kind of expansion half from the known operations like this. And this half is not here by mistake. Like whenever you go slightly below half, then all these local to global phenomena happen in high dimensional expanders. Real cohomology vanishes, whatever that means. The underlying graph's expansion is kind of inherited from the local neighborhoods. And all these things happen kind of whenever you go slightly below half. So this is actually interesting. Having that said, there are some beautiful constructions that do push it up to this like barrier of half. Again, here I will mention just two, though there are.
That it's not interesting. You mean that it's not interesting, getting out?
I mean,
the main applications of HDX.
For the main applications of HDX, it's not interesting, but I mean, it's a combinatorial question,
Yeah.
right? How to construct graphs with well-connected links.
Let's see.
Okay, I will believe you.
Yeah, believe me.
I'm blacking out and I don't want to search my references, but thank you. Yeah, there is also other constructions. Maybe I won't write them all down on the board, but I'll mention Chapman, Lineal, and Peled, Lee, Mohanty, and Young, and even Golovich, which I'll also mention later, has a construction along these lines that does something like this. So what about maybe random constructions? So one maybe random model is to try and kind of generalize the Erdős-Renyi model. Even in graphs, you kind of need to take logarithmic degree, but in higher dimensions, it behaves much, much worse. So for some dimension D, and any expansion that's below 1, you actually need to take kind of a number of vertices with a power that approaches 1 as you take the dimension to be higher. So even for dimension 2, you would need by a random model to take something that has average degree square root of number of vertices to get any kind of connectivity in the links. Maybe even up to some logarithmic term. I'm not sure if this is written anywhere. So maybe this is just folklore, but you can do the calculations yourselves. It's quite simple. We don't know of a random model that gives you something that's bounded degree. Kind of the state of the art here is these random geometric graphs that come from kind of putting points on a sphere. There we know that for dimension 2, you can get expansion that's like slightly below half with degree that's still polynomial, but kind of, if you take this epsilon to be small, the polynomial will be like also very small. And this is by Arsiki, Lee, Mohanty, from Young, I think from 22. So look how much effort we need just to go just below half, and we're not even close to getting to this. And now we're kind of approaching the constructions that I want to talk about in the second part of the talk, which are constructions that come from linear algebra. So first, there is this beautiful construction of Golovich that will give us any dimension and any expansion, and the degree will not be bounded, but it will be subpolynomial. So we get something like 2 to the log n to the half. And this alone is very interesting. I mean, I don't see this expression too much, right? We're used to like either polynomial or logarithmic. And what's nice about this work is that it's extremely simple. I will tell you about this construction. To understand it, you only need to know something about low rank matrices in F2. And this is also a Cayley graph. It's like very easy to kind of understand it. And so a big part of our project was actually to generalize this construction. So our construction is going to do the same thing, but instead of getting 2 to the log n to the half, we'll get 2 to the log n to the epsilon for any constant epsilon. And I think we can probably do sub-constant, but we haven't figured this out yet. It's just like doing some calculations. This is basically our construction. It will also be a Cayley graph. It does have some recursion to it, so maybe slightly less simple than Golovich, but still very elementary, and it will be relatively easy to describe. And one last thing that I'll say about this before actually doing it is that kind of the idea behind this construction is to rely on Golovich's construction, but to take a new perspective on it, and to actually look at this construction not as like one thing that you do, but actually more like a zigzag product or some kind of iterative procedure where you take an HDX and you kind of modify it to get sparser and sparser HDXs. So where are we now? Okay, we did an hour and I'm like half through my talk, so maybe 5 minutes break if that's okay. Usually somebody says
It's your
up to the
decision.
speaker, yeah,
It's
okay.
yours.
So I decide, but yeah.
Yeah, so maybe I'm trying to get back to this. I'm an expert, so I didn't.
Sure.
So like just looking at this table, it looks like the group theoretic constructions give you any dimension, for any dimension of the expansion, you get an optimal degree.
Yeah, like constant,
Like,
yeah.
Bounded, I don't know. if
Yeah, that's true.
But is it that like you're aiming for like some additional properties or just like different types of construction, like
Oh.
using?
Great, that's a beautiful question. I'm so happy that you asked that. Okay, first of all, I mean, if you just need high dimensional expanders in some applications, you can take this and this is completely fine. But as in expander graphs, I sincerely believe that if we learn how to construct high dimensional expanders from different sources, we will both learn more about these objects themselves and things that are adjacent to these objects and we really care about them. And I'll give maybe a personal answer that as a combinatorist, even though I can appreciate the beauty behind these algebraic constructions and I understand them to some extent, I don't feel that under the hood I really understand why these objects expand. Or I have not maybe a full understanding, and this comes from the fact that I don't work on groups all day. Like I do combinatorics, sometimes computer science and things like that. And so I would really like a more elementary construction that I know and I understand fully in this level and maybe can teach and so on. Also, I could argue, that once you have more simple and transparent constructions, if you maybe want some extra property from these things, besides being an HDX and bounded, maybe you want a routing scheme or, a way to like sample random paths or something like that. You can maybe think that more elementary constructions would kind of be more amenable to this tweaking and modifying.
So in some like applications, you might ask for additional.
Yeah, and in fact,
Having more elementary construction.
Sometimes applications pop up only after you have
Yeah.
a different construction.
Yeah.
that's
Okay, great.
That's true. Already applications popped up sometimes like we have some work from last year about property testing on using these high dimensional expanders that eventually led to these PCP constructions. And there suddenly you needed like a high dimensional expander that's also like simply connected, or at least has something to do with like its fundamental group. And then, you know, either these complexes have this property or not, but like if say we didn't know how to do this, like then we, you know, we need more tools in our toolbox to maybe.
Yeah, great, thank you.
So maybe 5
Right,
minutes. Okay, so let's start. I will repeat everything for Peter. Good.
You know, I asked about Kruskal.
Okay. So I want to tell you about this construction. And I already defined what a high dimensional expander is, which is kind of our goal object in the intro. But actually I want to shift things just a little bit and to kind of give you a variant of this high dimensional expander definition that we will use. And this variant will be very simple. Every place we have a set, we will actually switch it to a vector space. So I need to define a simplicial complex. So now I'll define a Grassmann complex. I need to define the dimension of the Grassmann complex. It will be the same, and also like links and so on. Let's just do this. So what is a Grassmann complex? So here it is. Suppose we have some finite vector space, which is going to be over F2, so maybe F2 to the n. So a Grassmann complex is just a subset of the Grassmannian that's downwards closed. So it will be some Y that contains subspaces inside F2 to the n. So I will write this to denote that this is a linear subspace. Okay, so some collection of subspaces, so that if I have a subspace in Y, and I have a subspace W prime inside this W, then also this W prime is inside Y. So again, entirely analogous to simplicial complexes, only subspaces. And I want this like downwards closure thing. And I will give an example in just a second. So now we can define things analogously. So Yi will be all subspaces of Y whose dimension is I. This time I have dimension, so I'm just going to use I here. The dimension of Y is just the maximal dimension of the subspace inside Y. And now I also need to define a link. So here I'm going to do a slight modification of what I did before. I'm only going to define the link graph. Okay, not like the entire link, but you can generalize this. So here's my link. Suppose I have some W in Yi, where I have I less or equal to D minus 2, so I will have spaces with 1 and 2 dimensions above it. So the link graph, which I'll denote by YW, will have the following vertex set and edge set. So the vertex set is going to be a subset of the lines in Y. So what are lines? These are just one-dimensional spaces. So let's say all U and Y1. So what is the correct thing to do here? In simplicial complexes, we looked at sets and we said something, vertexes in the link of S is together with S, it forms a set of size 1 more. So here we're going to say it's all the lines, so that together with W, it forms a subspace of 1 more inside Y. So when I say form, I don't mean taking union, I mean taking the span of W and U together. So these are the vertices. They're just lines that together with my given W give you something inside Y. And what will be the edges? So the edges will be pairs of lines And now, what are edges in links of a simplicial complex? They're pairs of vertices, which together with my given subset give you something that has size 2 more. So this time, I want pairs of lines so that together with my subset W, give me a subspace that has size 2 more. So I will give an example in just 1 second, but let me just spell out the definition of a Grassmann HDX, which is just going to require that all these things expand. So definition, a d-dimensional Y is a Grassmann lambda HDX if for all subspaces of dimension so that I can actually define the link graph, why the link is a lambda expandable graph. This is the definition, and syntactically it's very similar. Let's give an example. What do you say? Yes.
So basically, look at the link for W and take any U and it's just that like.
Yeah, and so they actually won't be connected, right?
Yeah.
That's true. That's a fair point. Like this is a phenomenon that you don't see maybe if you look at the vertices. Actually, that's good intuition. Let's see how this works in our example.
Okay.
Right? So, you know, in the high dimensional expander simplicial complex, we looked at like the complete complex. Let's look at the complete Grassmann complex. So Y that takes all subspaces dimension. Maybe I won't have notation for this. We will all understand. And let's maybe take the line that's spanned by the first standard vector inside F2 to the n. One like slight abuse of notation, we're an F2 to the n, so every line contains the 0 vector and one other non-zero vector. So sometimes I will identify between the lines and the vector that spans them. So instead of writing this set, it's just shorthand. Let's look at YV0. What are the vertices of YV0? Well, it's all the things that if I look at their span and the span of V0, I get something that's 2-dimensional. So these are actually all lines except V0, right? So V of V0 is taking all lines except V0 itself. But now, Peter, to your question, what are kind of the edges? So here is maybe an example, right? Suppose we have U, which is 0, 1, up to 0, U prime, which is maybe 1, 1, 0, to 0, and W, which is like 0, 0, 1, up to 0. And you can see that between U and W, we'll have an edge because together with the first standard vector, they have a 3-dimensional space, but these two are kind of equivalent to mod V0, so they won't. But the way I like to think about this is that, you know, you look at every W of dimension 2, this is capital W, that contains my line V0, and you can partition the vertices in the link, kind of mod V0, which is like, each part and put all the lines so that together with V0, they are equal to some fixed specific W. W0, W1, and so on. And in this complete Grassmann, right, two things that sit in the same part won't have an edge between them because they won't give me a 3-dimensional space. But whenever I have two distinct parts, I will put all edges because they will give me the 3-dimensional space, which is this plus this. And so this turns out to be, taking a complete complex, replacing each vertex with some cloud, and putting like complete bipartite graphs between every two clouds. Let me not write this down, but yeah.
So would this be like equivalent to saying that this is an expander, like the mod?
Yeah.
Zero graph is.
That's true. I'm defining it this way, but it's a matter of convenience. Okay. Okay. So kind of, you can probably believe me, right? That this thing has expansion. Or maybe write O because again I'm blacking out. This in the vertex case, it will behave roughly like 2 to the minus n, maybe up to some constant. And in general, this thing is supposed to be an expander for lambda that's like 2 to the minus n plus dimension. Okay, because all the links will kind of look like this in the complete case. Okay, so this is maybe an example. Oh, one last comment that I want to say. We had this like empty set in the simplicial complex. And here in this link definition, it also makes sense to look at the zero space, which is like our empty set. So like the zero space, right? The vertices will just be all the lines, and the edges will be, two lines that share a plane inside Y. So this is kind of like the link of the empty set, but like the analogy here. Okay. So I told you something about simplicial expanders, and then I switched up, and you can ask, why do I care about this vector space thing? I want to construct simplicial expanders. So I'm going to tell you, for this I will also need this kind of notation. So I will say that something is an n d lambda Grassmann HDX. I will not write this Grassmann, it will be clear. I will always use the letter Y. But this time I'm kind of changing the notation here, so you'll have to forgive me. So this time n is like the size of the ambient space. D is the dimension. This D will be the number of lines, and this lambda will say expansion. So I want to say this explicitly. Before this D was the degree of a vertex in the simplicial complex, and now I'm putting here the number of lines. Before this n was the number of vertices, now I'm putting the size of the ambient space. But let me justify this by telling you a beautiful construction by Golovich. So here's a lemma. Suppose you have some n d lambda Grassmann HDX y, then you can construct from it n d almost lambda. I'll write here lambda over 1 minus lambda simplicial HDX x, and moreover, the underlying graph inside this HDX is going to be a very nice Cayley graph whose generators are the lines in Y. So I want to write this construction for you. Maybe I write it over there. So given such a Y, how am I going to construct it?
Billion.
Yes, it will be an abelian graph over F to the n. You are not happy with this.
No.
You can leave. I see you want to leave the room. Okay, so the vertices are F to T. The edges are just going to be defined by the generating set, which are the lines inside Y, or formally the vectors that span lines inside Y. And it's going to be all pairs x and x plus v, where x is in F2 to the n, and v is in Y1. And more generally, if I want to look at I sets, I will just take X and add to it basis vectors from spaces inside Y. Okay, so now X is a vector and V1 up to Vi are an I-dimensional subspace inside Y. So this is like taking, I+1 points in general position, but so that if I move them to containing the zero axis by like subtracting this X, I won't get just any space, but I'll get an I-dimensional space inside my input Grassmann complex. Okay, so wonder if I want to actually tell you, okay, I'll tell you something about this lemma. I don't want to prove it formally, but one thing that you can see is that if you have some set S, you can see like that the linear subspace that's spanned by this basis doesn't depend on actually like the representation of X, of like choosing which point here is X and which points have the basis. Because for example, if I have Y, which is like X plus V1, then I can write this where, okay, the second point is like Y, but the first point is like also Y plus V1, and the rest are like Y plus V2 plus V1 up to, sorry, Y plus Vi plus V1. And kind of, if you look at this, then you see that the span of V1, V2 up to Vi is the same span of like V1, V2 plus V1, V3 plus V1 up to Vi plus V1. So all I'm saying is that you can, oh, actually, here. All I'm saying is that kind of given S, it is well defined kind of the space WS that looks at the span of the basis of the space that we use to construct this set S. And it's kind of an observation that the link of X as point S is going to be the link of Y at point WS. And this, for example, when do I have some X plus U that's inside here, right? This is if and only if this U together with the rest are in Y I plus 1. And kind of by definition, this is if and only if this U is inside this space of W. Even if you haven't followed this, the upshot is that the links of every face except the empty set are really the links that I see in Y. Like it is an absolute isomorphism. And kind of the reason that I have here, not exactly lambda, but something that's maybe slightly larger than lambda, is because when you want to analyze the expansion of like the global graph, you use kind of a trickle down technology, maybe Oppenheim's theorem, that says that like if neighborhoods look like lambda expanders, then you like get this global type of expansion. But even if you haven't followed me, I'm not going to prove this. Let's just take this as the given theorem.
Is it maybe better than that?
Maybe. Good question. Like also, I mean, you can ask if generally it's better, and you can ask if like for specific construction it's better, and I don't know either answers. Yeah. So what's the upshot of all this? Is that now we have actually a new goal. Okay, which is constructing n the 2 to the log n to the epsilon lambda Grassmann HDXs.
So how does this jive with if you try to make a Cayley graph, which is an expander, you can't have a bounded degree of this. So you are at the threshold of what you can do there? Or are you making a new
No,
construction there?
Thank you, that's a good question. Like, Cayley graphs over f2 to the n, I need a logarithmic degree,
Number,
right?
generally.
Here, this is not a logarithmic degree, right? It's like not 2 to the log log, it's 2 to the log to a small power. And it's a good question. We have kind of some initial directions whether we should get a better lower bound if we take the dimension higher, but actually I like, for example, for 2 dimensions, I don't know. This is an open question whether you need more. Great. So this is my new goal, constructing Grassmann high dimensional expanders. And now we're going to take advantage of the fact that we're using vector spaces and kind of play with it. But actually, before I want to tell you about our construction, I will need to tell you about Louis' construction, which is the main idea why we actually came up with this lemma. You know what, maybe just I'll give one more comment for the experts, maybe only, that if you want a high dimensional expander from these Grassmanns, you can also like kind of look at the spherical building version where you just look at the poset and then take some of its sides, and it will also give you an HDX that looks kind of like a sparsification of the spherical building. It will be less symmetric, and so I don't want to really describe it here, but kind of, I feel that there are many interesting things about these objects. Some of them we actually don't know, so these are like much less studied, so maybe we can do interesting things with them still. Okay, but if you haven't followed that, never mind. So this is our goal, to construct these. And now let me tell you about Golovich's construction, because it is very simple. So here's Golovich's idea. Let's look at n, and let's assume that it is a square. So it's like m times m. And now let's think of f2 to the n as matrices with side length m. And also let r be some integer greater than 0, which we will see kind of determines degree and expansion. Here's Golovich's construction. Lines are going to be matrices whose rank is R. I will tell you what the planes look like in 5 minutes, but before that, we can already calculate the number of lines here just by R rank matrices, right? So every matrix of rank R, I can write it as, R tensors of rank 1 for these AJs and BJs, right? They're in F2 to the M, not F2 to the N, right? And so the number of lines is upper bounded by 2 to the 2rm, because I need to tell you about 2r vectors of size m to tell you, the matrix. And in fact, this is an upper bound because some of them will be less than rank r, but it's also tight. So at least asymptotically. So already we kind of see that like for f2 to the n, which is like 2 to the m squared, you get something that looks like this. So like changing parameters, if n is like 2 to the m squared, you kind of get a number of lines, which is like 2 to the, let's write O of log n to the square root, where this O kind of hides this R constant. So already we can see where like Louis' gain is, but now I need to tell you what the planes are and the higher dimensional spaces. Let's start with maybe the plane. So I will write it like this. So we're looking at all spans of 2 matrices. Actually, before this, maybe let me ask, what do I even need for this to be a plane, right? I need that all non-zero vectors will have rank R. So M1 should be of rank R, M2 should be of rank R, but equally importantly, their sum, M1 plus M2, should be of rank R. So I need some way to construct this plane so that this will happen. And I could have just taken all such subspaces But to generalize this, we will need some more structure on them. And so this is what Louis does. He says all M1 and M2, so that there exist three matrices of rank R over 2. So I will require that the rank is a half. I will require, for reasons that we will see soon, that the sum of the three, the rank of the sum is the sum of the ranks. You will see soon why. And I want that M1 will be equal to sum of two of them, and M2 will be equal to sum of the other. A1 and A3, and A2 and A3. So first of all, this condition together with this condition will promise us that the rank here is summing two R over 2 matrices with kind of trivial intersecting row and column sums. So this will indeed be of rank R. This will be of rank R, and their sum, I don't require this, but it's true, will also be of rank R. It will be A1 plus A2. So there's kind of beautiful combinatorics that's happening here.
Minus.
It's F2.
We're over F2 to the, right? So plus and minus are the same. Yeah, like A3 and A3 are canceling out. That's like the point here. And great, so these are the planes, and just telling you this without going to higher dimensional spaces, already you will get here like a two-dimensional HDX just by kind of looking at this line versus planes thing. I want to tell you about the higher dimensional spaces, and then you can kind of think about what you need to generalize here to like construct higher dimensional spaces so that, you know, all vectors inside will have rank exactly R. And you can maybe draw this as a picture where this is like A1 and A3, and this M2 is kind of A2 and A3. And like the reason that everything came out to be R is that because like if I sum like over these lines, I will get like something that has the same length. This is just a picture, it's not saying anything new. But kind of if I maybe want to add a third matrix so that any linear combination of them will have rank R, then you can kind of think that maybe I need a matrix where its decomposition kind of shares half of this A1, half of this A2, half of this A3, and half of this A4, or half of something, sorry, that's kind of outside everything else. And now, if you kind of look at any linear combination of these, you will see that you will also get something that has rank R, as long as this thing is like something that appears in the decomposition here that has like half the rank. So maybe let's even do this. Write this for 3 formally, and then I will generalize for I, even though the formula itself is not very interesting. Like I want a span of M1, M2, M3, so that now there exists, instead of 4 minus 1, 8 minus 1. So it will be A1 up to A7 with the same kind of properties. So the rank of every one will be like R over 4. The rank of the sum is going to be the sum of the ranks, which would promise me that like a sum of any subset will have the correct thing. And so now I want, maybe I'll write this in a new line. Now I want M1, M2, and M3 to have like the corresponding A's, so that like every linear combination will contain exactly 4 of them. So I think here I need 1, 3, 5, and 7. This is just so you can appreciate this. It's not very important what the exact things are. 2, 3, 6, 7. And you can kind of try to observe that any linear combination will have exactly 4 of these. So here maybe you should see this pattern of like the Hadamard code maybe, right? That like I want that any linear combination will have like the same number of A's, and so I will kind of index these so that like the linear, like the Hadamard code will have the, is appearing here. So I don't, maybe, actually in our work, we kind of study this connection of these complexes to the Hadamard code and more general complexes. So it's interesting, but it's also kind of technical to state, so I don't want to do it. But any case, I'll just say that like you can define the I-dimensional subspaces analogous. So it's kind of existing A's. Should I write this down? No, right? Good, but just maybe believe me, the rank of every A are divided by something, rank of sum is sum of ranks, and every M is kind of composed like this.
Can I ask a question now?
Yeah.
If you instead kind of wrote it in a more implicit way and just said, I want all the span of the M1 to MI, so that every element in the span has rank R.
Yeah, so this will give you actually more, even plain it will give you more.
Right.
And actually, if you only look at lines and planes, this will work too. With higher dimensions, I don't know.
So it's harder to analyze?
Yeah, this is also going to give me a really nice structure inside the links that actually Louis observes and exploits, and then we kind of take it and generalize it. It kind of helps us view the link as something that's tensorized, because somehow if you fix M1, you know about like these decompositions, and then like the M2s that neighbor it share like exactly half of the decomposition and don't do something crazy. Like matrices and ranks are like, in general, they behave kind of crazy. So you need some extra structure. Yeah, but you know, once I said here Hadamard, maybe you can say, oh, I like other codes. Maybe I can try to do it with other codes. Like for this specific purpose, we didn't manage to do anything, but I mean, you can try and define these things and they're interesting, I think. Like maybe, yeah. Good. So this is Louis' construction. Maybe I will just say in like 2 minutes. I'm not going to describe why links expand in this construction, but kind of if you only look at like the link of the zero subspaces, so lines versus planes, you can see that maybe if you go from M1 to M2 and they kind of share this like half intersection, then after doing a constant number of steps, like M1 and you know maybe this M4 that you do by taking a few other steps in the graph, the row and column spaces here will intersect trivially, like with very high probability. So we're like almost at a uniform location. And if you kind of believe that fast mixing is equivalent to this expansion, you can kind of get expansion from this. But I don't want to do it. Maybe it's not. So maybe you can just kind of believe that this graph itself is maybe kind of dense and expander-like. Anyway, I want to tell you about our construction. And syntactically, our construction is also going to be very simple. We're just going to take Louis' construction, and instead of looking at it as something idiosyncratic, where you only take, you know, spaces and matrices, we're going to look at it as kind of an input-output process by itself. So here's our construction. We're going to take as input some complex, Grassmann complex, let's call it Z, which is going to have some parameters, 2 to the m, d, some degree, and some lambda, which we will require to be small enough. And our output is going to be some y, where, okay, so now like we need to see what's going on here. So here it will be d to some kind of small power. I think maybe I'll just write here 0.01 instead of trying to calculate this. So we're going to lose in the expansion. We are going to have more lines, something that looks like d to the dth power here. The dimension is going to suffer. It's going to be even logarithmic, but we're going to gain by increasing the ambient space immensely, from 2 to the m to 2 to the m squared. And how does this kind of go? You kind of set R to be d over 4. And now we're going to make this small syntactic change to Lewis complex, where are my lines? These are the planes. Oh, these are my lines. Where now my lines are going to be only the m's whose row span and column span are inside my input complex. And when I will construct higher dimensional spaces, in addition to the requirements that I will have, I will require that the row of the sum of A's and the column spaces, this sum of A matrix, will also be inside Z with the appropriate dimension. So if you think of Z as being the complete Grassmann complex, you will recover Louis' construction from this. Of course, this is a generalization, but we also kind of rely a lot on what Louis did in its complete Grassmann complex analysis. But the point in writing it like this is that now you can put different things in the input here and sparsify more. So for example, if instead of the complete Grassmann complex, we put what Louis already did, then we will get something that's even more sparse here, because the number of lines will grow somewhat, but the ambient dimension will grow a lot. And so, for example, if we put Louis' complex inside here, then you will get something that will look like n, which is like 2 to the m to the 4th, some log here that kind of depends on what dimension you took as in your input, let's call it maybe d prime. And here you will have something that looks like 2 to the O of m, where this O of m kind of depends on the input dimension, but let's think of everything as like constants that are very large. And the lambda that you will get will also kind of depend on the input dimension. So kind of writing this differently, you will get like 2 to the log n to the 4th. And now you can kind of recurse. You are losing, right, in the dimension. So in the first step, you take log. In the second step, you have log, and so on. So it's maybe like a log star iterative process that you can do. But definitely, like for any constant amount of times you want to repeat this, you can. And that kind of explains why you will get here some epsilon and not a square root. So it all comes from like just repeating iteratively some process.
Explain why this makes sense to define it as well.
This?
Yeah.
Yeah, I have an explanation, but maybe you won't be, like maybe other audience won't be so happy because it, like in simplicial complexes, you can kind of look at the faces complex where now like vertices are sets and you connect two sets if they have like some relation, like there's somehow disjoint. So it's kind of, you know, you think about vertices and then you make them like, and then like instead of vertices in your original complex, you look at some other complex that has sets and you somehow inherit expansion. So I can't take, you know, subspaces and define them as vectors and then do that. But matrices is kind of going around this. Like I would like, you know, a Grassmann complex where my vertices are subsets and something happens for planes and so on. I don't know how to do that, but I can somehow encode pairs of subspaces using matrices. So this is kind of why I feel that this thing makes sense.
What was your question? Why it's expanding? Why this recursive maintains expansion? What did you want to know?
I mean, why this construction? What's going on?
What's going
Yeah,
on?
okay. Okay, maybe I will say something. Okay,
Take it offline as well.
Yes,
yeah, I can.
Let me say one sentence. You're clearly going to say more than one sentence. All that Gorovich uses in this proof of expansion of this, you know, this complex is that the full Grassmann complex expands. That's really all he uses. And the observation here is don't start from the full Grassmann, start from any expanding complex. If you only use the expansion of the given complex Z, then you can do it. You can do it again, exactly what it is. It's just the way putting the Rosenkranz
I mean,
space.
if I understood correctly, Golovich's construction didn't have the red part on the board.
Yeah, but you can have the red.
Talk about row span belong or column span belonging anywhere.
Yeah, but you can imagine that Golovich had it in his construction, only that Z was the complete Grassmann. He loves any matrices,
Okay.
all matrices, right?
Right.
But he uses only the fact that the complete Grassmann expands.
Okay.
Okay, so you replace it by any expanded Grassmann.
Yeah,
Okay.
that's a good point. I wanted to maybe complement what Avi said, and another maybe way to look at it is like this local to global paradigm that often people use in expansion, where you kind of observe that even if you require these things to happen, then like all these link graphs and so on, they will look like some big graph. Inside it, you will find like local parts that look like the complete Grassmann, and we already know that they're good expanders because Louis already did most of the work for us. And then you kind of squint a little and you notice that like this is very amenable to like some local to global analysis, because the way these things are kind of spread is what is really determined by this Z thing. So kind of you can identify derived graphs that come from this Grassmann, like links inside Z, inside this like links inside matrices that are hiding. You can like think about them as being some quotient or something. So kind of you observe that all this, the construction and Louis' analysis could be viewed as itself as some kind of local to global analysis. And then once you see this, you say, oh, within my local to global analysis, instead of just looking at like these inclusion graphs in the Grassmann, I look at inclusion graphs that come from some other place. For example, this Z, I will get the same type of expansion. It really comes maybe from understanding what in the analysis could kind of be modularized to something else. Okay, I mean, I don't know if it's a good answer. Like, I definitely want to generalize this even more, and I don't know how.
I have a question. Is this local to global that you talk about the Garland?
Yeah, it's the Garland rest.
All right, I just want to understand what you have.
So like, yeah, like specifically we're using a theorem by Madras and Randall, which kind of in Garland's work and other subsequent works in his area, it was used kind of implicitly, but yeah, it's exactly this type of local to global arguments. Yeah. Okay, I don't think I want to actually like tell you why this link expands more than I did, because I don't think I have too much time. But I do maybe just want to kind of conclude this talk by giving some open questions that probably some of you are guessing, but even not, I'll just say them. So kind of one open question from the first part of the talk is just give me elementary bounded degree HDXs. So something that maybe, you know, you come up with some clever linear algebra, or again, some like zigzag that doesn't come from these things. This is, I think, very interesting. A second one that polylog degrees. Anything better than the table that I gave you is already, of course, very interesting. Second, all right, question mark. Second, even in these like Grassmannians, because of like Louis' theorem, you can see that the number of lines must be at least logarithmic, because in particular, you get like an expanding Cayley complex from these Grassmann complexes.
Logarithmic in 2 to the n.
Yeah, right, like size of the dimension of the ambient space. The size of the lines must be, yeah, must be yeah.
Okay.
Right, so, you know, maybe construct, you know, and the right here of the poly log n lambda HDX.
Dimension.
Sure. Let's even put your dimension 2. Of course, this is in fact, I mean dimension 1, just lines and planes where I have a logarithmic number of lines, and this is a lambda expander.
In the Grassmann, you call it dimension.
Oh, right.
The
It's
lines
line-
and planes, yeah. Right.
You're right. Just lines and planes that expand. Right. This is true. And you can also ask, is there a lower bound that's better than what you can get just by kind of saying something about the expansion of the Cayley graph that you get? Maybe you can get
Bigger
the
than
polylog.
log here.
Yeah, I wrote here polylog.
Even bigger.
What's the Moshkovitz-Raz parameters, do you know?
So theirs doesn't expand according to this definition.
Doesn't?
Like you take a field and then you take a subfield, and then like the subfield doesn't span the large field to the end. We can talk about this later. It's, like technically you don't get this, but the fact that this what that they have don't expand according to my definition doesn't mean, this is not my definition, but this definition, it doesn't mean that it's not an interesting concept.
Hey, supports a low degree test.
Yeah. It's what I meant. So it doesn't mean it's not interesting. It's just it's not helpful for this specific application. All right, this is maybe number 3, that maybe you can't do this. Maybe there is a lower bound, and I think that I will conclude with this for now.
Question.
But you use matrices, why not like Richard tensors?
Oh, beautiful question. Some of the analysis that actually already Louis does relies on the fact that even if I write my matrix like this, I have many ways to decompose the matrix into other like A primes and A prime prime that that don't share any like row and column from these A's or something in the space. And this is used for expansion. And once you look at 3 tensors, then you don't have this. Like most 3 tensors actually have a unique low degree decomposition, and this can't be used. Having that said, kind of if you look at what happens if you do this construction twice, then the objects that you actually get are kind of 4 tensors. Only these 4 tensors somehow have also a lot of like low rank decompositions.
Right, so that's why I was thinking you just do a 4 tensor directly and maybe better, or?
Yeah, so you
No,
have,
but all of these are for
Yeah.
they were constructed, they can't simply. So
Right, no, so you.
they are really matrices of matrices, and you use, so for each level, you have this freedom of.
No, what I'm wondering is, would you get like better parameters? You don't.
yeah, it's no, actually I don't know. I mean, it
don't know
could be
how
that
to do
you could identify maybe another subset of 4 tensors that has a lot of decomposition, and you can maybe define lines and planes like that. It's a good question. Yeah.
So here you start with an abelian group of 2n, right?
Yeah.
And then you pick basically, I can think of y1 as being generators, right? So at the lowest level, this is just a Cayley graph, but then you have a way of going up and getting more stuff.
Yeah.
Do you have any natural candidate constructions where you could replace f2 to the n by any other group, say a symmetric group, for example, and have some kind of natural construction that would
Yeah, so
allow you to
okay.
pick
I mean,
order generated of some kind? I mean, I'm trying to see if one can.
I mean, okay, like other fields, you can do things analogously, and this is like very easy. And you can also try to do this with abelian groups. In fact, even with groups, I think that you can maybe try to have like a generating set or a symmetric generating set or something like that, and trying to take, generators of subgroups. We haven't we haven't like really exhausted this direction. It could be that like just
That's something that resembles what Conlon did.
did he? I believe you. I do.
Some generators that have relations among them, and he looked at the Cayley graph.
Yeah, that's in that generality, yes. Anyway, it could be that like using some non-abelian group, you can gain something by like this affine thing. It's just that I'm not sure how technically you do something like this. I mean, also you right like part of the point here is that you go from like this poset of subspaces to something that looks simplicial, and you can kind of ask, how do maybe posets of subgroups look like or something like that, and I think they are not always symmetric, and generally they're maybe slightly less understood, but you can maybe try and find specific examples where these things work well.
But there's nothing natural right now.
No, nothing. I thought about this. I don't see anything natural to do, anything.
How does the degree, either in Louis' construction or yours, depend on the dimension?
Depend on the dimension. Oh, that's a great question. I admit that I don't have the exact expression, but like if you think about this repeatedly m times, then you'll have like a tower, like 2 to the 2 to the 2 to the 2 m times. Where in the first one you'll have like 2 to the d, where it's like.
What about just for Louis' construction?
Yeah, so for Louis' construction, you start with with the complete Grassmann of high enough dimension d, and then you kind of, and the degree will have like d in the exponent. So here you'll have doing it twice, it will have like 2 to the 2 to the d in the exponent. Yeah, but okay, I should say I'm very bad with thinking about these parameters. So there might be something slightly else going there, but like what I do want to emphasize is that this is a very nice theoretical construction. But
You don't get double exponent or tower in the degree. No, you just get polynomial in the.
No, but here you go
polynomial in
for-
d in the degree. But 2 to the d is just 2 to the d squared.
No, it's 2 to the 2 to, like, because you're doing here like log and log log and so on.
Yeah, then you gain because you exponentiate by something much smaller. You don't get it out.
Okay, you should believe Avi in this one. Okay, in my head, I have to make some of these parameters constant. I'm sorry, because otherwise I find it hard to grasp. But what I remember is that the dependence on these is more horrible, but maybe Avi's right, so.
Zander, you see that in this iteration, one step you raise to the power d, but it goes down logarithmically in every step.
Maybe I'll say this. What I mean is that if you look at like the eventual dimension that you want, like let's call it d2, right? And maybe you want to do 2 iterations to get to this d2 to get whatever you want. Then like when you look at what you needed to have like in one iteration before, because this was a log of the input, and this should be like 2 to the d2. And now what do I get, right? To get this, right, I need, I think 2 to this, right? So I need like 2 to the 2 to the.
Oh, you mean the initial degree?
Yeah, the initial.
Not how much you suffer in the process.
Like what I meant is that if you want epsilon to be like 1/4, you need to do this twice, and then you'll have like 2 to the 2 to the something. If you want epsilon like this, I don't know where I have it. Like if you want this like log n to the something to be 1/2 to the m, then you will have like an m tower exponential. That's. Yeah.
So your actual bound then is something like exponential in log n to the 1/log star.
Yeah, so I want to say yes, but we haven't done this in the paper because you're taking here a quarter, and somehow we're always assuming that things are large enough, and I didn't check what breaks if you do this like a non-constant number of times. But in principle, I think you can push this to 1/log star.
Okay, thanks so much.